All right, so questions?
That's definitely the server, just doesn't let you
CTEX server is totally different from our Linux server.
Yep. We're trying to get into the old CTEX server.
It should still work, as far as I know, but it's a different login, right?
I mean, whenever I try to get in, it gives me a software board or something.
You're just trying to cheat.
Oh,
Yeah.
Let me look at old programs.
Yeah, because
Yeah, it should be student ID for login, and then password should be your regular Clark password.
Well, I can't even, I'm using Quibi since I'm on Windows. I can't even get into the login section. Just the shell pops up, but then it just...
It doesn't ask you for a username?
Yeah.
we're trying to go back and get the is problem.
Yeah.
I think you know why.
All right, so yeah, let's talk about PA2, because people have already started on this.
So I think the server's different.
So we know what prime numbers are, right? Prime numbers are numbers that are only divisible by themselves and 1. So 2 happens to be a prime number, but that's the only even prime. But 3, 5, 7, 11, 13, 17, 19, 23, these are prime numbers, okay? 25 is not because it's also divisible by 5. 1001 is not because it's also divisible by 13. So how do you know if a number is prime or not? Well, one way is just to see if anything divides it other than itself in 1. Okay, so let me talk about the goal of PA2, and then we'll talk about strategies for doing it. So it turns out that if you think about even numbers bigger than 2, right? 4 can be written as 2 plus 2. 6 is 3 plus 3. 8 is 3 plus 5. 10 is 5 plus 5, 12 is 5 plus 7, 14 is 7 plus 7. It's also 3 plus 11. What I'm doing here is I'm writing down each of these even numbers as a sum of 2 primes. Okay? And it turns out, to a pretty high case, every even number that you can think of can be written as a sum of 2 primes. Often more than one way, right? And so there's a conjecture called Goldbach's conjecture. And a conjecture is different from a theorem. A theorem is something that can be proven. A conjecture is something which somebody states they believe is true, but for which there is no proof. So Goldbach's conjecture says any even number greater than or equal to 4 can be written as the sum of 2 primes. Conjecture, Goldbach, yeah, B-A-C-H, like the musician. And so this has been, studied numerically up to large numbers. You just keep generating even numbers, try to write them as sums of primes. It's been studied mathematically up to extremely large scales, and people generally believe this is true, but nobody's ever proven it. Okay, it's one of those number theory things that's easy to state, but really hard to prove. But they've proven that if there's a number, an even number that's not writable as the sum of 2 primes, it's got to be really large, and it's got to have, pointy hair and green eyes or something. They've got all these characterizations of what could possibly be a counterexample to this, and it's a pretty small space, but still nobody has proven that this is always doable. So programming assignment 2 is playing with this conjecture. And basically you're going to write a function that if you give it an even number, it will write that as the sum of 2 primes. And then you're going to test this by taking an even number, starting with something around 1,000,000, and generating a table of how those numbers can be written as a sum of 2 primes. So you're going to write your program in C or C++, and it should run starting with the number 2,000,000 up to 2,998,000. That's 500 even numbers starting at 2 million, and for each one it should write out something like this, right? 2 million equals some number plus some other number where those are prime. Okay. And if you happen to come across an even number that cannot be written as a sum of two primes, you're going to become famous. Okay, so that's why it says call the newspapers. But every number in the range that we're looking at should be writable as a sum of two primes. So that's what your programming assignment 2 is going to do. It's going to just generate this table of how each of these numbers can be written thusly. Okay, so how do we do this? Let me give you first the absolute worst way to do this. This way is so slow that it will not finish by the time the assignment is due if you start running it right now. Okay? So don't do this. So let's write a do-it function which will write out the number n as a sum of two primes. Okay. For I equals 3 to n. For j equals 3 to n. If I is prime and j is prime and I plus j equals n, then print out our stuff, closing our curly brackets. That will work. That is incredibly inefficient. Okay, this is taking every odd number from 3 up to n, and every odd number from 3 up to n, and for every pair of those, seeing if the two numbers are prime, and if they are, seeing if they add up to our number n. Okay? It works, it's logical, it makes sense, but it's really, really inefficient for the following reasons. One, most of the times, the values of I and j we get here are not going to add up to n. Okay? So this is, if this is the number 2 million, this is going to loop roughly 4 trillion times. Okay? It's not going to be tractable. So do not do it like this, even though that makes sense. A better approach is for I equals 3 to n, right? And go by twos, because we're only interested in odd prime numbers, right? If I is prime, and if n minus I is prime, then we're all good. Then we can print out, hey, this is expressible as this prime number plus that prime number. Okay. And this is plenty efficient if you have a good prime number checker. Okay, so does that make sense? So don't do a pair of nested loops. Run one variable through odd numbers. If that number is prime, see if n minus that number is also prime. If it is, you've got your answer for how to write n as a sum of two primes, right? N is just equal to I plus n minus I, and we just said both of those were prime. So now the question of generating primes. And you do not need to get very fancy with this. So is the number n prime? If n is divisible by I, it's not prime. If you come all the way through this loop and you never decided n was not prime, then it is prime. So as soon as you find a divisor, just return. Don't set a flag and keep looping. You only need to know if there's at least one divisor. So if you find a divisor, just return a 0 right then, say it's not prime. If you get all the way through the loop, it is prime, return a 1, or whatever you're returning. Okay, that's the basic desert island, nothing but coconuts and palm trees way to test to see if a number is prime. The way you make this more efficient is by tweaking this upper limit. So do we have to check numbers all the way up to n? How far do we have to go? You only have to go to the square root of n. Okay? Logically, you only have to go to n over 2 because anything bigger than that is not going to divide n. But it turns out you only have to go up to the square root of n. Because if I is bigger than the square root of n, then n divided by I will be smaller than the square root of n, and you would have already found that number. So you want to test divisors between 3 up to and including the square root of n. Okay, that's all you really need. Make sure you start with 3, not 1. 1 is not a prime number. That's just by definition. So start checking 3 to see if it's prime, and if it is, see if n minus 3 is prime. And if that is, then you're done. Your number n is written as 3 plus n minus 3. Otherwise, try n equals 5. That's prime. N minus 5, if that's prime, right? And this is efficient enough. Okay, you don't need to store things. Technically, you only need to try dividing by prime numbers. That's going to require you to generate primes and save them somewhere. You can do that, but it's really not necessary. Okay, this is good enough. Good enough that you won't see a delay when you run it. You won't be waiting for it. Okay, so that's pretty much all of this says. Write a function that tests to see if a number is prime. The easiest way is to try to divide by every number from 2 to the square root of n, or you can just test odd divisors, because we're only interested in checking odd numbers. Rather than dividing, you can use the modulus operator, right? So is n divisible by I? This is just saying if n% I is equal to 0. Right, so that's the same thing as this. So that's the remainder when n is divided by I. That's the modular arithmetic we started talking about on Monday, or Wednesday. All right, and that's it. So, so what I want you to turn in, I want you to write your program, run it, confirm that it works, and then I want you to submit a PDF. Your PDF has to contain your source code. Okay, that's the thing I'm grading, followed by a copy of the output when you run your program on numbers from 2 million up to 2,001,000 minus 2. So it's going to be a C program or C++ program source code, and then a whole bunch of things that look like, 2 million equals this, 2 million and 2 equals that, and so on and so forth. You only need to find one sum. You don't have to find all of them. Okay. So make a PDF, upload it by the due date. Yeah?
Are there more programming assignments after this one?
Not for this class.
So why do we need access to the Linux server?
Why do you need access to Linux server?
Yeah.
Just for doing PA1?
Okay.
Because that was the machine I tested it on. PA2, you can do it on any machine you want. All right, other questions on this? Oh, I don't know. Anybody know? Sounds familiar. March 9th. I know, that's a lifetime away. All right, I'm going to post an announcement on Canvas later on today, but for those of you who haven't heard, Scott Koss is teaching a 2-credit machine learning course in spring. It's going to be Mondays, I think from 3 to 5 in here. So it's CSE 280, I believe is the number. And it should be a fun course. So if you're interested in that and you got 2 credits to spare in your schedule, go for it. for it. But I'll post an announcement with the details. All right, any other questions? All right, well, let's keep going with number theory. So let's do some board work. So break your solves into groups. So we got about 25 people. You can probably do 5 or 6 groups. In each group, grab one of these, and I've got several problem sets on here. We're just going to work on the first problem set for now.
Yeah, you don't have to log in. I know, right? Yeah. Both on.
Yeah, on the board.
Was this also homework 5?
No.
Shoot. I did all of this.
I did?
I did all this.
Where'd you find it?
I think you had it posted under homework 5.
That might be part of homework 5.
Oh,
yeah.
okay.
Well, let me double check. Hold on a second.
Did you look up homework 5? Does it look familiar?
It's like,
Yeah, I think. Okay. I'm pretty sure this is working.
Oh, you're right, you're right.
Oh, well, okay.
Okay, yeah, that's cool.
Okay.
That's yeah, they're on the other
It's
pages.
actually everything.
Yeah, okay, I remember this now.
Except you got a few extra problems.
Yeah.
So,
All right, so question 1, we're just playing with divisibility. Find 5 examples of A and B such that A divides B. So if you've got multiple people in your group, you can each find a different example. Don't forget up dog.
so you're saying you want to write it or you want me to write it? You can write it. Okay. So five examples of A and B such that A divides B. Yeah. So what would be an example? What's an example of A and B such that A divides B?
4, 2.
A divides B. So we want 2, 4.
Is it that 4,
Because
2?
so what this notation is saying is that
Are these the
it's saying that if so or maybe writing it more generically.
So first thing divides the second thing. So like your last line is claiming that 3 divides 9.
So that's what this means.
Yeah, you're right, you're right.
You're good. Everyone in mind. Hey, no cheating. Look at your own board.
Isn't it 4, 2?
You're a lot.
4 divided.
I think that'd be fine. Plus 10.
Yeah, it goes the other way. So this says 10 divides 5.
That's opposite.
Yeah.
So this is
So this goes into that way.
So see, basically that's what that means.
So,
I actually wrote it backwards. I meant to say. So
we need to make sure it is.
that's why I was like,
That's okay.
I actually wrote that wrong. Find 5 examples of A and B such that A does not divide B.
just add 1.
Well, yeah.
All right, then question 2, do the opposite 5 examples where A does not divide B.
All right.
Does? What?
Nice. If A divides B, then A divides BC falls under C. So right up front here. Are we doing number 3?
And then do number 3, yeah. So number 3 is approved.
C is subset.
Does this work too?
They gave us
1 times 10.
What is that?
One count? Number 3.
the definition of this, which would be
Yes, you want to prove it.
Okay, I want proof.
Yes, you want to prove it for any A, B, and C.
Now this works, so just pick it something like Q subset. That's our definition. Now we want to multiply C on both sides. Remember, we're trying to prove this.
Oh. This is definition.
So here's what we do. Right? So we have BC, right? Equals A, CQ. What is this?
Yeah, prove you want to show
That's
us
just
all.
A times R. R is integer. So,
Well, I don't know, but I was thinking that thing that I was before.
let's, actually, I don't think I skipped any steps, right? So, we proved that that's the definition. That's the definition of, I can say, 3 def of height. Def of, I don't like that because I was thinking of 1, but def of whatever. Yeah, I tried to use a pipe and I can def of height. Cool. Next one. You guys remember that if A divides B and A divides C, then A divides 2B plus 2C.
Yes! When you completed something, code worked.
When the code worked.
Yeah, it worked for one time. That's the one time he's like, yes! Are we doing 4 as well?
It's 1, 4.
We're doing all of it.
Most of it.
This. Oh.
And by the way, just a point of notation for like number 2, when you say 6 does not divide 9, write it like that. Right, just put a slash through the pipe to say does not divide. That's just a notation.
It's fixed. It's good to know.
We might have to talk about office hours, but I was wondering if 16
Okay.
is it still technically possible to do that?
Absolutely.
Okay.
Yeah,
Just wanted to
yeah.
make sure.
Yeah, don't sweat over the grade, right? Keep up with the work, do reasonably
Yeah.
well on the final, you're good.
Okay, okay, thank you.
This is how we start. Trying to get to here.
Yeah.
What do you guys want to do?
Okay, so 8 times some integer is
We could use the chain rule here, I would easily just.
No, this isn't, remember, this isn't B divides C, then we change. Yeah. So no, we're not actually changing.
Oh, sure, yeah.
We just know that A is a factor of B and A is a factor of C.
Sure.
So here's what I think. This would be my idea. So I kind of like looking ahead, right? Maybe we could write it in more section.
okay, so 3 times so
We remember that modular arithmetic. So something like this. Let me just write an example. A divides 2B. If A divides B, we like intuitively know that's always true, right?
Yeah.
The reason is that's the same thing as writing A divides B. We switched to Monte arithmetic. That's the same thing as writing a mod times, this is a 0, right?
Yes.
So times a mod 2. It's a 0 every time.
Yes.
So intuitively we understand that,
Yeah.
right? And intuitively going that that's going to also work with addition.
Right.
The reason it works with addition is this is going to be 0, this is going to be 0. So you're adding 0 to 0. Right. 0. So now we just need to prove that. How do you guys want to prove that? How about we start with this part? What if we just try to bring A to B?
Since we have a definition here, we'll say that's
You just spread that all over by the end of this word.
Yes.
Yo, is that Yo! Wait, no, it's not. It's not about this has to. It's a J.
2B equals A times C, right?
There says C, right,
Yeah. Yes.
And then if you have the definition of divisibility,
Let's do the
Yeah, that's what I think.
3C.
From that one final walk or whatever it was. Dude, it was everywhere. And nothing was correct. I can't find it. That was from
yeah, I mean, that would be your reason for writing that. That's what you were trying to show. If
That's not my problem.
this, then.
Sounds like a single piece function.
Okay, so you get to practice that more.
Okay, so we proved, okay, so this, now we just need to prove that we can use associativity, right, to say that this mod.
So you got A divided B definition.
Yeah. Let me write it like this. So from the definition, right, I just kind of. So I put definitely like here, definitely definition. You have A times some integer.
So you're trying to.
2B equals A times some integer, therefore, just from the definition how these work. But it's still right.
Yeah, so then it becomes A.
So
it doesn't
I'm thinking of what you're saying. So you're saying that this is not the right? Okay, so you're saying that it would be clearer if the 2 is pulled outside? But then we wouldn't, because we want to get it in our definition form, which is A times some integer, right?
Yeah, that makes sense, yeah.
Okay, so this is just some integer.
Oh, sorry.
Perfectly, A divided B is
Okay, so 0, 1, 0, 1. And it's just need to basically add them.
I can actually make
Well,
some
remember for modular, that you can also, this was the multiplication version. If you wrote the associativity as some sense, you can write something like.
Yeah. 0, 1.
It's B mod A.
Basically has some form that says A.
Yeah, so I would write that down. B is
Plus
equal to
B mod Q or C equals and that's just a definition, that's associativity, right? So that's sort of our keys on all there. Now we can, knowing that, so I'm just going to write associativity, so I can write that. A mod mod.
We can substitute 8 times 2 for.
No, right. Would that be associativity or distributing?
Which is also useful.
Yes.
It's like distributing.
Look beside the inside. Just look on the inside.
Down there, just like that last.
That's a 9.
It's distributed from this. Not big now. And this is sort of what it looks like, but we know that this is a distributive property, right? And we knew this is 0, and we know this is 0.
I would only want to ask one of this, it might feel like we're jumping a little bit, but it's pretty straightforward.
I was thinking of like X1 resource map, which is like 6 plus, no, 5 plus 7.
Oh, yeah, it might make it. We could do that, I guess. There. You simply need to go right.
How long are they?
To be back plus
Yeah, there's not that one.
and we know it wasn't true. So we're gonna do that. Our next one is, we're just going to turn it into shape as our
That's right here.
Oh no.
So, for this one, we're just going to, this gives us various values, and we have to say them true or false. So I'm going to write them all out. And someone can help me. Yeah,
So BC is A times that.
So we can show.
Let's
Our section. Logically equivalent to? Well, you can also write it right. J in the last one. Yeah, it's J. The amount is 0.
Well, the definition of that is the same thing as showing.
So, just to review, you're asking the syntax. So this, being equivalent to that, means that 13 mod 11 is the same thing as negative 9 mod 11. It's not, this is how they write it. I like to think of it in your head like this. 13 mod 11 equals negative 9. That's the same thing. So this is the same thing. So it's just they write this logically equivalent thing, and they just don't write the mod. So this is with respect to modular arithmetic.
Is it another one like the?
No, not a
Yeah. So for example, 7 mod 2 equals 1, right? Because 2 goes into 7 3 times.
Oh, okay.
6. So you can write it like this: 2 times 3 equals 1. 7 goes into 7. This is our mod. That's how it goes, basically. So these we can look at and say, okay, is that true? Does this have a remainder? I'm adding it to I'm sorry. We're asking, 2 mod 8 have the same remainder as 26 here. That's what we're asking. 2 mod 8. So what's the remainder of 2 mod 8? Actually, it has a remainder of 2, right? Because it's saying how much more we divide it as many times as we can. In this equation, it might actually help. I'm going to write this equation. 2 mod 8. Basically this. What should I write that? I want to write it generically. So that would be called the quotient. Quotient equals divisor.
Oh no, these are different. These are connected.
Plus remainder. So we write this like so we can
Extra credit.
K A mod B. So the same thing, right? That would be that A equals B times some constant C plus 3. And A mod B is equal to kind of have that in our heads as we go through this. So what's 26 mod 8? 2. What's 2 mod 8? 2.
Why is that?
Because if how many so like I'm asking you a question. I want you to put 8 to 2 as many times as you can. How many times can you put 8 to 2? 4. 0. Okay. How many times can you take 8 and shove it into 2?
Yeah.
So like say you have two like a box that's like 2 squares big, and I give you something that's like 8 squares big, right? That's not 8 squares, you know, whatever. That's like the problem. And I want you like, how many times can you fit this in there? Well, I can't fit this in there. Okay, 2 up there. Yeah, good question. That's what makes sense. So, how many times can you fit into 2? None. 8's bigger than 2, so you have 2 left over. You couldn't subtract from 2 at all. It's like writing, I want you to like subtract 8 from 2 as many times as you can. And end up with a positive number or 0. Yeah. So, like, you want to have a 0 or a positive number.
So who did the proof for 4?
I did.
Okay.
You don't like it?
Can you talk us through it?
Yes. So we just took our definitions, our hypotheses, our definitions, and then we multiplied both sides of this by 2.
Okay, so wait. What are we trying to show?
We're trying to ultimately show that A divides 2B plus 3C. Given A divides B.
Okay, so A divides B and A divides C, you want to show it divides 2B plus 3C.
Yes.
Okay, so if this, then that. So the way you do any if-then proof is you assume the hypothesis, which is this and this, and you try to argue to the conclusion. Okay, so you can assume this, that's the hypothesis, you can assume that, that's the hypothesis. Okay. And these are the definitions of what it means to say A divides B. It means B is A times some integer called Q. C is A times some other integer called R. Could be the same as Q, could be different. Okay. So we know these two things are true. And we're trying to show that this is a multiple of A. Okay. So no other place to go really other than let's write this using this version of B and this version of C. Okay. 2B is 2 times A times Q, so A times 2Q. And C is AR, so 3C is going to be 3 times A times R. And if you write these in this way, you can see that each of those is a multiple of A. And now just add 2B and 3C together and equal that, right? And you're going to have, well, A times 2Q plus A times 3R. Right, so that's A times the quantity, 2Q plus 3R, which means that A divides that expression. Okay. So it's really the same thing as question 3. It's just more complex stuff. Yeah, but it's the same approach.
I should have probably written more math stuff. I used a lot of, like, well, we know it's distributed, we know it's this.
Right.
It wasn't in school.
Is that
Cool.
What are you doing here?
I was just explaining.
Okay, cool. Okay.
That like, yeah, 2 mod 8 is 2 mod 8 is 2. Still have this guy.
Right. Oh, cool.
Cool. 2 mod 11. 2 mod 11.
So A divides C divides.
Now we're getting the negative. Let's get
All right.
So what's 13 mod 8? And what's negative 9? So this is where it helps. This is where it helps to have this equation. Right? So we're going to try to write negative 9 equals 11 times some constant plus some remainder.
So 2b plus 3c, just add those together.
So negative 9 equals 11 times something plus some remainder, and our remainder is bounded by.
Everything in here is negative. Okay, that's the definition of a divisor.
So our remainder has to be negative.
Isn't it minus?
It wouldn't be.
Yes, should be minus 9, right? My gut saying has to be positive though.
Well, yeah.
Oh, it's always smaller than, like, it's always one smaller than the.
Yeah, I'm just saying the definition is minus 9, yeah. So we're asking this question. Negative 9 was 11 times something plus some remainder. Well, what can we do? Times minus 1? Plus 2? Is there everything we can do?
Yeah.
Well, we did it times 1. Every times 1. Then what would our remainder be? Be negative 13. We can't do it. Yeah. So there's only one. But that was the thing we did. The remainder is. What about we did it by 0, then we'd have to add negative 9. Which
Is two.
nope.
Well, no, it doesn't.
I know it's like intuitively.
Where did you get this from?
And what?
So it's when you're doing positive, it works like that. It has to basically be between. Yeah. We could take the absolute value. Less than or equal to the absolute value.
Well, to me, since like the constant c can be like any integer, then the remainder shouldn't have like.
The remainder has to be, we could say it like this. The absolute value of negative 9 must be greater than the absolute value of the remainder. And we know that intuitively, because if you have, right, if you remember here we're trying to show 8 squares into 2.
Yeah.
Or say we're doing that one. Say
Oh,
we're
I
having
see,
to try
I
to go this
see, I
way.
see. That's what
Well,
we're doing.
yeah, you're never going to have like 3 squares left over, right? Because that means you have 2 you can put it on. So you always have.
So if
less.
remainder equals 9, then there's no remainder.
So remainder's got to be 1 or nothing. It can't be the whole thing.
I see.
Otherwise you can shove it in. But I'm getting fuzzy with the definition of this because obviously, like this is what I want to do, and that's I
But
know
then
that's
minus 8 is bigger than minus 9.
what's that? If it's negative, flip the sign. Trying to think how this works. Do we have the definition? Someone write down the definition from their notes? We went over this last lecture. It has a name for the theorem. I wrote it down.
Division, I know it's kind of. Modular?
It was something that said, remember, he said we're going to base like all our number theory on this, but we're not going to prove it. Yeah, something to do with modular, but it was.
Yeah.
Yeah, I know. Back in
It always says like the remainder must be like from 0 to.
Divisibility. The division algorithm. That's what it's called. The division algorithm. So, yeah. X times 3 plus y. 0 is less than the remainder, less than b minus 1. That's the way I wrote it.
But it didn't say the b is minus.
Yeah, it didn't say if the unit is negative. So we're just gonna say if it's negative, we just add 1 because that's true.
That one that's minus 8.
Yes, then it's minus 8. We don't want it to be less than minus 8. We want it to be greater than minus 8.
Let's
So,
see, yeah, because this one you have to add.
we want a positive remainder, right? So we're gonna say we're just gonna take the absolute value. they have plus one, because I know that's right. But I know that's true. But anyway, main thing, we want a positive remainder whose absolute value is in between the absolute value of this and 0. Like intuitively that makes sense, right? You want to end up with like 1 square left over, 0 squares, not negative 18 squares. Right?
For some reason, when you calculate minus 1.9%.
Yeah, because it is true. We know it's true. That's what we're proving, right? Because the remainders too, right? So that's what I'm saying. Your answer is not only correct; it's like the only answer that satisfies this.
So we really care about the absolute value of the number.
I'm not exactly like I don't want to say something wrong. I know this is worse. The remainder must be positive. We know that. So if the quotient is negative, then we're going to take the absolute value of it. That's just like a rule I'm making up. There's probably a better way to state it. Nick can tell you that.
That's what I'm asking about.
Yeah, but like this is true if it's negative. And if the quotient is positive, then we can just write 0 less than equal to. Quo minus 1. It's a really bad quo. This is when it's positive. That's for a plus, that's for a negative. So first statement. So we know this is 2. Same thing twice. Oh, it's 6. So it's just true. What's negative? What's negative? What's negative 1 like? So we could write it like this. Negative 1 equals 3 times something plus. And the remainder has to be between.
We brought so much. Yeah, don't know that.
Yeah. 3 times negative 1?
If they still stands true, so it should be 3 plus. No, negative 5 plus 1.
We're doing it this way.
Yeah,
I'll do more of this. I'll post it in the notes channel.
Negative 1 plus 1 equals 0.
Kind of follow shape.
Remainder has to be 1.
Like it says
Do you think if you
Remainder has to be 0.
That's think about that too.
Remainder has to
I'll
be
still have
0.
it raised.
Yeah, me neither.
Oh, here's where I missed. It's the, it's what we're dividing by. It's 3. 3 minus 2. That's
Oh, you know what? I think I know why we do 2e. Because it's like a bar.
And then over here, what's this negative 9?
So we replace
11?
Well, 11.
b, I guess that
11 is 1.
abstract. For some abstract reason, we can also
So forget it.
by
Absolute value.
it's 2 cube.
It's very simple.
Same thing for 7.
We just take the mod value.
A 3r. So makes it
So negative 1 equals 3 times something, and some remainder. And the remainder has to be less than 2, or equal to 2. So, that's what you're saying? That's negative 3? Those 2? Negative 1. There's no other way. That's the only way. If you ever get away, then you know it's the only way because of the division algorithm. We're just in an algorithm. Which ones do we have left? This guy? Oh, we gotta do minus 5, right. So we write minus 5 is equal to 3 times something plus some remainder. What do we do? Minus 2? Perfect.
This is his first one.
And the remainder here is 2.
It's his birthday. Not much of a
Negative 5, is that a negative 5?
Yeah.
Negative 5. No, so let's just, we know that negative 5 is because we did. So that's negative 1. So what's negative 2 1? Well, let's make a guess here. We know negative 1 month.
That's so funny.
We have a remainder of. That's right. Negative 2.
Anytime that a search number of like negative 1, so we have a remainder of 4. Either we are worded the other one is there's 1 for negative 5.
All right, so let's talk about the rest of these and then go on to the next page. But mostly I want people to work on those divisibilities and then work on those proofs, and I think people have got that.
Does he? How do you know? I'm not sure. What do we do?
All right, so I don't have to go through, so if you want to sit down, you can, because we'll talk for a while. I don't have to go through examples for the first two, right? I think people are square on that. And the proofs, I think everybody got those. So let's talk about question 5. And you may not have gotten to this yet, but that's okay. This is looking at modular equivalences. So determine whether these are true or false. First one says 26 is congruent to 2 mod H. Okay, there's a few different ways we can do all of these, right? The first one is to try to figure out what 26 is modulo 8. In other words, write 26 as something times 8 plus something, where this remainder is bigger than or equal to 0 and less than 8. And that one's pretty easy to guess at, right? It's 3 times 8 is 24 plus 2, right? And 2 is definitely the same as 2. It's congruent to 2 modulo 8, so this is true. But there's another way we can do this, and this is what this last question would have asked you to prove, but we're not going to actually do that. If A and B have the same remainder when divided by m, meaning they're congruent to each other, modulo m, then their difference is divisible by m. So all of these we can just simply say is 26 minus 2 a multiple of 8. 26 minus 2 is 24, that is a multiple of 8. And if you asked is 2 congruent to 26, you could say, well, is 2 minus 26 a multiple of 8? Well, that's negative 24, and yeah, that's a multiple of 8. It's 8 times negative 3. So in these cases where this number was pretty close to 0, right, we can do this different ways, but we can always take the difference. So 13 minus 2 is 11. 11 is a multiple of 11, so this is definitely a true statement. 13 minus negative 9 is 13 plus 9. That's 22. That's a multiple of 11, so that's true. Negative 5 minus negative 1, that's negative 5 plus 1. That's negative 4, not a multiple of 3. So this is false. And if we wrote this out, negative 5 equals something times 3 plus something. So what do we put in here to get this something bigger than or equal to 0 and less than 3? That's correct, but we want this plus part to be bigger than or equal to 0, less than 3. Negative 2. So negative 2 times 3 would be negative 6 plus 1. Okay, so that tells us negative 5 is congruent to 1 modulo 3. And then negative 1 is something times 3 plus something. What do we do for that? right? Negative 1 times 3 is negative 3 plus 2 gets us up to negative 1. So negative 1 is congruent to 2 modulo 3. So that tells you these are not congruent to each other, negative 5 and negative 1. But their difference is not a multiple of 3 either. All right, negative 5 and negative 2. Negative 5 minus negative 2 is negative 5 plus 2. That's negative 3. That is a multiple of 3. So that's true. And then this one, there's a few different ways to do it, but the easiest way is probably see what this is congruent to modulo 10. And modulo 10, you just get the last digit, right? Because when you divide this by 10, a million is evenly divisible by 10, and you got 7 left over. And 1,000 is evenly divisible by 10, and you've got 7 left over. So both of these are congruent to 7, so they're congruent to each other. The other way that I usually do if nobody's like watching me is if I want to know what negative 1 is congruent to, I just keep adding 3 till I get to the number I want. Right? Negative 1 plus 3 is positive 2. Negative 5 plus 3 is negative 2, plus another 3 is positive 1. And there I'm done. And if you're starting with a number bigger, you know, a number that's too large, just keep subtracting. 26 minus 8 is 18, minus 8 is 10, minus 8 is 2. It's congruent to 2. So you can count down from positives or count up from negatives. And each of those numbers you get is something that this is congruent to, and you just do that till you find a number in that range between 0 and your modulus minus 1. Does that mostly make sense? Yeah?
Can you explain how negative 9 mod 11 is positive 2?
How 9 mod 11? Negative 9 mod 11, yeah. So you want to write it as something times 11 plus something, where this something has to be bigger than or equal to 0 and less than 11. So I'm probably going to do a negative 1 times 11. That's negative 11. And I have to add 2 to get to negative 9. So that's what it's congruent to. Right? And if I did my other trick, I would just start at negative 9 plus 11 gives me positive 2. So those are congruent. If I add another 11, I get 13. So 13 and negative 9 are congruent. If I add another 11, I get 24. So 24 and 13 and 2 and negative 9 are all congruent. And if I subtract 11, I get negative 20. That's also congruent to each of these. And this is really the punchline for modular arithmetic, is that we get a whole bunch of numbers that are congruent to each other. If we're working modulo 5, every integer is congruent to either 0, 1, 2, 3, or 4. Right, so in particular the numbers 0, 5, 10, negative 15, negative 5, those are all congruent to 0. The numbers 1, 6, 11, 21, 101, those are all congruent to 1. And we can break all the integers up into these 5 big groups of numbers. Everything in this group is congruent to 0, it means it's a multiple of 5. Everything in this group is congruent to 4. It's 4 more than a multiple of 5. Everything in this group is congruent to 2. It's 2 more than a multiple of 5. And we take all our numbers, every possible integer, positive, negative, 0, goes into one of these 5 groups. And if we know how to operate on these congruence classes, we can operate on the things inside these groups. And we can make statements about the whole set of the infinite number of integers just by making statements about these 5 things, these 5 collections of numbers that are congruent to each other. And so we can prove lots of things. Let me see if I can drum one together in my head in 15 seconds. So prove that for any integer n times n plus 1 times n plus 2 times n plus 3 is divisible by 4. Okay, so for example, n equals 5. 5 times 6 times 7 times 8 is whatever that turns out to be. That'll be divisible by 4. And we can multiply this out and get a 4th degree polynomial and probably factor a 4 out of it. But we can show this more easily by using modulos. Because for any number n, one of 4 cases is true. Case 1, n might be congruent to 0 modulo 4. Then n plus 1 is congruent to 1, n plus 2 is congruent to 2, n plus 3 is congruent to 3. And let me call this product P. And so P would be congruent to 0 times 1 times 2 times 3, which is just 0, which means that product's divisible by 4. But it could also be the case that n is congruent to 1 modulo 4. In which case n plus 1 is congruent to 2, n plus 2 is congruent to 3, n plus 3 is congruent to 4, and so our product is congruent to 1 times 2 times 3 times 4, which is congruent to 24, which is congruent to 0 mod 4, because 24 is divisible by 4. And you can do this in the other possible cases. And whatever integer you pick, it's got to be congruent to either 0, 1, 2, or 3 mod 4. And we can show that in each of those cases, this product is also congruent to 0 mod 4. And that's enough to prove this theorem, that this product of 4 consecutive integers is always a multiple of 4. And we don't have to take every possible integer and multiply it by the next 3 integers and show it's divisible. It suffices to just do it for 4 particular integers based on what it's congruent to. And there's a whole bunch of cool things we can prove using that approach. All right, switch of gears. So it's greatest common divisor. When you're learning to do fractions in school, you end up talking about greatest common divisors, right? If you want to do 2/3 plus 5/7, we can't just combine these because the denominators are different. So we need to put them over a common denominator, right? So we do something like 2 times 7 plus 5 times 3 over 21. Right? So that's the least common multiple of 3 and 7. The other direction, you have a fraction like 35/21, and you want to put it in simplest form, right? So how do we do this? What's the trick? I mean, anything we can divide the top and the bottom by, this is going to be the same value, right? So if you wanted to find 120ths, that's the same thing as 50/10ths. It's the same thing as 25/5ths, right? It's the same thing as 5/1. So what do we divide the top and the bottom by here to get a simple form?
7.
Why 7? It's the biggest thing that divides both the top and the bottom, right? Here we divided by 2, well that's perfectly fine, but it doesn't get us the simplest form. To get the simplest form, we need to divide the top and the bottom by the biggest thing that divides both of them. Okay, that's the greatest common divisor. So 35 divided by 7 over 21 divided by 7, that gets us to 5/3. So the greatest common divisor of two numbers equals the largest integer q such that q divides a and q divides b. And let's just think about positives for today, okay? Let's not worry about if any of these things are negative. Let's just think about positive integers finding the greatest common divisor. Okay, so there's an algorithm for finding the greatest common divisor of two numbers, and this is called Euclid's algorithm. So Euclid's algorithm for finding a greatest common divisor. Suppose we want to find the greatest common divisor of well, let's just do 35 and 21. Okay, here's what we do. We write the larger number as something times the smaller number plus something else. So this should be, the remainder when you divide 35 by 21. So 35 in this case is 1 times 21 plus 14. Okay, here's the cool part. The GCD of 35 and 21 will be the same thing as the GCD of 21 and 14. So once we've written 35 as something times 21 plus something, we bring these over like this. And we say, let's write 21 is something times 14 plus something. Okay, in this case it's 1 times 14 plus 7. Bring these over again. 14 equals something times 7 plus something. Okay, in this case it's 2 times 7 plus 0. Once you get that 0, this is your GCD. Got it. All right, so let's do that again. Let's do GCD of 150 and 90. So 150 equals something times 90 plus something. So 1 times 90 plus 60. 90 equals something times 60 plus something. So 1 times 60 plus 30. 60 equals something times 30 plus something. 2 times 30 plus 0. There's your GCD. So you're basically taking the remainder and trying to write this smallest number as product of the remainder plus something else. If you switch the order of these, it still works, by the way. If I start off by saying 90 equals something times 150 plus something, well, 90 is 0 times 150 plus 90. And then when I bring those down, I'm saying 150 is something times 90 plus something, and I'm right back to where I was. Okay, you'll code this in 223 for your first assignment. So that's a nice algorithm for finding GCDs. And if you start off, where one of these things is a multiple of the other, you're going to say 100 equals something times 25 plus something. Well, it's 4 times 25 plus 0. There's your GCD, as you would expect. And if one of these is prime, or maybe both of them, like 31 and 7. So 31 equals something times 7 plus something. So that's 4 times 7 plus 3. 7 equals something times 3 plus something. So that's 2 times 3 plus 1. Okay, keep going. 3 equals something times 1 plus something. That's 3 times 1 plus 0. There's your GCD. Okay, so don't stop till you have a remainder of 0. And then that last number that you were taking a multiple of, that's the GCD. So 25 and 9. So 25 is 2 times 9 plus 7. 9 equals 1 times 7 plus 2. 7 equals 3 times 2 plus 1. Keep going. 2 equals 2 times 1 plus 0. There's your GCD as 1. So when the GCD is 1, it means the largest thing that divides both of these numbers is just 1. And certainly if these numbers are prime, we know they're not divisible by anything except themselves in 1, so the GCD will be 1. But here we have two numbers that are definitely not prime, but their GCD is still 1. Okay, so there's a term for this. If the GCD of A and B equals 1, A and B are called relatively prime. And they're not necessarily prime in the full-on prime sense, but with respect to each other, they have no factors in common other than 1. And relative prime numbers will be important later.
I wish I would have known this is a bit further.
Yeah, right. All right, so homework 5 for this course. It's a 40-point homework because it's got lots of questions, and we're actually working through most of this as a group. So the first few questions are ones that we did in class. Question 6 is using Euclid's algorithm to find the greatest common divisor of these pairs. So you can work on that one, right? And then question 7 was on that sheet, but we didn't necessarily get to it. Some people did, but it's looking at divisibility. Modular exponentiation, Fermat's little theorem, we will go over on Monday. Okay, these are ways to do what would normally be very large calculations, like finding the remainder when 101 is raised to the 221st and divided by 23. Okay, and we can do that with very few calculations if we know a few tricks. So we'll go over those on Monday. That'll give you enough material to do your homework for Wednesday. And then the quiz next Friday will be on number theory, so it will be these kinds of things.
Do you want the blue packets back?
No, hold on to the blue packets if you can and bring them with you on Monday, because we'll probably do more problems from there. All right, have a good weekend. Somebody left their engineering pad. Is that yours? Okay.
Did you mean to put all those pages as our homework on the blue packet?
I think so.
Because only the first page shows up in the PDF. Unless I'm not reading the PDF.
No. All the things here should be on the blue sheets, but the blue sheet has stuff that's not on here.
Okay.
Yeah.
So 9 questions you meant is long.
Yeah. This is the homework. All right. There's more stuff on the blue sheets that's not part of the homework.